Hello and welcome to Diplomatic Derivatives. In today's video, we will be continuing with the Permutation and Symmetric Group series where we are now on part 4. We have already uploaded part 1, 2 and 3. So check those videos because we have explained in detail what is a permutation, types of permutations and product of permutations, transposition, inversion and so on. So those concepts are very important before we move on to the Symmetric Group S₃ and S₄ along with alternating groups A4, A3 and A4 and the future theorems. So check those out first. Also, I have uploaded other videos on Lagrange's theorem, cosets, Cayley's table and other concepts including generators of a cyclic group and so on. So those videos are also very important in pure mathematics. Check those out along with applied mathematics. I have started the series which I will be continuing in the future. So check all of those out. And for now, we will be continuing with the symmetric group. So let's see what is a symmetric group. Now, the set SA of all permutations of a non-void set A is a group for the product of permutation and is denoted by G is equal to SA, O. Now, in simple words, what does this definition mean? First of all, we see here that we have a set A. So you will be given a set. Let's suppose that set is 1, 2, 3, right? With the help of 1, 2, 3, you will be able to make certain permutations. So let's suppose one permutation is 1, 2, 3, in which 1 goes to 2, 2 goes to 3, and 3 goes to 1. So this is one permutation. Another permutation you can make is 1, 2, 3, with 1 goes to 3, 2 goes to 1, and 3 goes to 2, right? So this means that you can make a number of permutations, right? So basically, by now, or by all this time, we have done permutations on its own, right? Now what we'll be doing is that all those permutations will be grouped together under an operation, and that is known as a symmetric group. Okay, so for a particular set, all the number of permutations when grouped together under an operation, that group will be known as the symmetric group. All right, so when we talk about a group, it means that it will follow the group properties, and in the very first video we have explained what are the group properties, that is closure, associativity, identity and inverse. So if all these 4 properties are satisfied, therefore this symmetric group, this group of all the permutations is basically a symmetric group or a permutation group. So it's the same thing, either you say permutation group or you say symmetric group, it's the same thing. All right, so the first property, which is closure. So basically what you do is, let's suppose you take a permutation F, like this is, let's suppose this is F, right? The name of the permutation inside the symmetric group, okay? So one permutation is F, one permutation is G, one permutation is H, are all elements of a symmetric group SA. We will call it a symmetric group only when the 4 properties are satisfied, right? So let's suppose we take 3 permutations F, G and H. The first one, under the operation F of G, the product of this, let's suppose the operation is a product, so the element that comes after the operation belongs to SA, so it's closed under this property. Then associativity, that is F of G of H is equal to F of G of GH, which is equal to F of GH. So again it will be closed under associativity. Identity, element exists, F of I is equal to F, and then inverse, F of F inverse is equal to identity. So if 4 properties are satisfied, it will be known as a permutation group. All right. So a group of permutation of set 1, 2, 3, so on till n is called the symmetric group of degree n and is denoted by Sn. The order of this group is n factorial, that is OSN is equal to n factorial. What do we mean by this? So when you have a symmetric group, till now we said it's SA. Let's suppose we say that either it's A or n. Okay, so that n, let's suppose we have n is equal to 3. Right, so it will be S₃. What does this mean? This means that the set from which we are getting the symmetric group has 3 elements. Okay, so that set, let's suppose that set is 1, 2, 3. So how many elements are inside the set? 3. So the symmetric group formed will be S₃. And now we want to know that how many elements are inside this symmetric group. Okay, not in the set. We want to know that how many elements lie inside the symmetric group. So how do we get that? That we get from this 3. What are the elements of a symmetric group again? The elements of a symmetric group are the permutations, right? So how many number of permutations are inside the symmetric group, we get from this number over here, which is 3. So that will be 3 factorial, so n factorial. All right. So we see an example here. We have the set 1, 2, 3. It's called a symmetric group of symbol 3 and is denoted by S₃. So the symmetric group formed from the set will be S₃. If A is equal to 1, 2, 3, so how many permutations are there? 6. How do we get that? That is n factorial. Alright, which is 3 factorial equals to 6. So what is factorial? Factorial means you will multiply the number starting from 1. So if it's 3 factorial, it will be 1 into 2 into 3, which is equal to 6. So the number of permutations inside this symmetric group will be 6. Alright, so let's suppose your symmetric group is S2. So the number of permutations inside S2 will be 2 factorial, which is equal to 1 into 2 is 2, so you will get 2. Right? Now how do you make those permutations? So since it's a set having 2 elements, the set will be 1, 2, right? So you make this first 1, 2 and its function, its mapping with 1. This is the image, right? 1, 2. Now how many options does one have? One can either go to 1 or one can go to 2. There is no other option, right? So in the first case, 1 goes to 1, 2 goes to 2. So you get this mapping, and this mapping is known as the identity mapping. For this, make sure you check out the video, the first part of this series, in which we have explained what is an identity permutation. Okay, so in that you will be able to understand that when 1 goes to 1 and 2 goes to 2, that is each element goes to itself, the image is same as the element, right? Then that is known as the identity permutation. Okay, then in the second case, 1 is going to 2 and 2 is going to 1, right? So how do you write this? It will be 1 and 2. Okay, the image of 1 is 2 and the image of 2 is 1. This is the second permutation that you can get. And then there is no other option. One can only go to either of these, right? It won't be going to any other element. So you don't have any other option left. So these are the only 2 permutations that you can get inside S2. Similarly, in a very similar manner, you are going to do for S3. So the element number of permutations is 3 factorial, which is equal to 6. So how do? You write 1, 2, 3, 1, 2, 3. 1 can go to 1, 2 go to 2, 3 go to 3. That is identity. Again, 1 has another option going to 2. Then 2 will go to 3, 3 will go to 1. Similarly, next option for 1 is 3, so 2 will go to 1, 3 will go to 2. Now 1 does not have any other option. Even 2 and 3 do not have any other option. So these are the first 3 permutations that you get. In the next fourth case, when you take 1 to 1, then 2 and 3 will have different options. So 2 can go to 3, 3 can go to 2. Similarly, next one, take 2 to 2, so 1, 3, 3, 1. And then take 3 to 3, you get 1, 2 and 2, 1. Right? So now you don't have any other options left. Now nothing else can happen. So that's how you stop. So now how many permutations did we get? You got 6 permutations. Alright? So now we just gave names to them. So the first one is identity, which is how do you write it? 1 to 3 on top. So 1 mapped to 1, 2 to 2, 3 to 3. Then in this second case, 1 goes to 2, 2 goes to 3, 3 goes to 1. In the third case, 1 goes to 3, 2 goes to 1 and 3 goes to 2. In this one, when 1 goes to 1, 2 goes to 3 and 3 goes to 2. Again here 2 goes to 2, 3 goes to 3. Right? So that's how you keep writing them, and you have given names, so it's easier for you to write. In the next slide here we see that S3 is equal to row 0, row 1, row 2, mu1, mu2 and mu3. So how many permutations are there inside S3? 6 permutations. Okay. So in the previous slide we saw the first one, which was row 0, in which each element was mapped to itself, right? So that is the identity. So row 0 is the identity in S3 over here. Okay, so row 0 is identity, row 1 is 1, 2, 3. Again, in the previous video I have explained that how to write these cycles, right? In part 3 and in part 2 and part 3 both. So in that, check out how to write cycles. So from the permutation you can write cycle like this: 1, 2, 3. The row 2 was 1, 3, 2. Then mu1 is 2, 3. Mu2 is 3, 1, 3, and mu3 is 1, 2. All right. So these are the cycles that we get for this symmetric group S3. All right. Now, since this is a symmetric group, so you can make a Cayley's table, right? For the Cayley's table, I have uploaded a video where I have explained in detail what is a Cayley's table. All right, and in that video you can see clearly how do you write the elements in the Cayley's table, and then after writing the elements, what are the results that you can infer from the Cayley's table. So that really is very important. Check that out as well. So the link is going to be in the description box. Okay. So from this particular example, you can see that you have these are the elements, that is row 0, row 1, row 2, mu1, mu2, mu3. You write all of them in the row and in the column. Then identity is equal to, so in the identity lane you just write each element as it is, and then the next one 1 2 3 and 1 2 3. So when you find the product under the operation, okay, whatever the operation here is, with an operation, when you perform the operation with 1 2 3 and 1 2 3, you get 1 3 2. Again, for the products, watch the previous video to learn how to make products. Okay, so you find the product here and you get 1 3 2. Then 1 2 3 with 1 3 2, you're getting identity. Remember this. 1 2 3 with 2 3, get 1 3. 1 2 3 with 1 3, you get 1 2. Find the products and you fill the entire table. Okay, now is the part where you learn what do you get from this table, right? So in this table you see that the inverse of 1 2 3 is 1 3 2. That is, you have 1 2 3 over here and you have 1 3 2 over here, and what is the product? You're getting identity, right? This means that according to the inverse property of the groups, the fourth property which is inverse, that is f dot f inverse is equal to identity. So if f is 1 2 3 and the answer has to be identity, what will be f inverse? 1 3 2. So this means that 1 2 3 and 1 3 2 are inverses of each other. Okay, when you look at the other rest of the elements, you see you get one identity here. So again it's 1 2 3 and 1 3 2. Another identity you get here, which is 2 3 with 2 3. So this is what you're getting. You're getting, this is 2 3 and 2 3. Similarly 1 3 with 1 3, and here you have 1 2 with 1 2, right? This means that, what does this mean? That these elements are self inverses. So the inverse of 1 3 is 1 3, inverse of 1 2 is 1 2, inverse of 2 3 is 2 3. So these cycles are self inverse. Okay, or in other words you can say these are what? These are transpositions, because the cycle is, length of cycle is 2, right? So the transpositions are self inverse. Or you can also say another thing. In the previous video we saw that what are even and odd permutations. This is a transposition, and every transposition is an odd permutation. So the odd permutations of S3 are self inverse, and the even permutations are inverses of each other. Okay, so this is what you infer from the Cayley's table. Alright, now in this slide what we see, we are trying to find the number of elements of order 2. Okay, like you have a symmetric group. Now you want to see how many elements are having order 2 and how many elements have order 3. Okay, order 1 is just identity, right? Identity is the only element which will have order 1. The rest will be 2, 3, 4 and so on. Okay, so in this one, how do we find? First of all, we know the order of the group itself, which is 3 factorial for S3, right? For S4 it will be 4 factorial. Okay, now the number of elements of order 2. Now we have a formula for this, for finding the number of elements of order 2 and number of elements of order 3. So without, like, why are we using this formula? We need this formula because without knowing the elements itself, without knowing how many elements will be there inside, like without knowing what are the elements inside the group S3, like for example in the exam they just give you question, what is the number of what are the number of elements of order 2 inside S3 and order 3 inside S3. They don't give you the group itself. Now obviously you know that these are the elements, right? But how many of order 2 exist and how many of order 3 exist? For that you will need a formula. Since S3 is a small group, it's easier, you can memorize it. But S4 is bigger, so you won't be able to remember all the elements, right? Then this formula will be very useful. So I will just explain the formula for this particular group. Okay, so what is the formula for finding number of elements of order 2 and number of elements of order 3, then number of elements of order 4, and so on. How do you do that? You take this number, that is n, okay, this is 3 here. So what do you do with 3? You will take 3 and write it in different forms. So 3 can be written as 1 plus 1 plus 1. 3 can also be written as 1 plus 2. And then 3 can be written as 3 itself. These are the only 3 possibilities, right? Either 1 plus 1 plus 1 or 1 plus 2 or 3 itself, right? Now, what is the LCM of 1, 1 and 1? It is 1. What is the LCM of 1 and 2? 2. What is the LCM of 3 itself? 3. So in this step what you do, you find the LCM of each of these. So LCM is 1, here LCM is 2, and here LCM is 3. So from this 2, you will get the number of elements of order 2, and from this step you will get the number of elements of order 3. Okay, now is where you use the formula. So what do you do? In the formula you will use this number itself first, okay, that is 3 factorial divided by, now what we are doing, we are finding the number of elements of order 2. So you write 3 factorial divided by, for order 2 the equation is 1 plus 2, right? So first you take 1, you write 1 here, raised to the power of what? Power will be how many times 1 came in this equation. It came how many times? 1 time. So power will be 1. In the bracket, this 1, which is the power, so 1 factorial. Alright. Then, sorry, this is not plus. Okay. This is multiplication. Okay. So, for 1 we did this. Into, next is 2. Raised to, how many times 2 came? It came 1 time. So it will be 2 raised to 1 into 1 factorial. Okay. So this is the formula. So 3 factorial is 6 divided by, this will become 1 into, this will become 2. So 1 into 2 is 2. 6 divided by 2 is equal to 3. So the number of elements of order 2 is 3. And we can see that in the group itself, how many number of elements are there of order 2? 1, 2 and 3. Similarly perform for the next one. So you take number of elements of order 3 will come from this equation, which is 3 itself, right? So you take, first you take this 3 factorial divided by 3 came 1 time, so 3 raised to 1, 1 factorial, which is equal to 6 by 3, which is equal to 2. So you get number of elements of order 3 is 2, which is evident here. How many number of elements are there of order 3? 2 elements, right? So that's how you find. For example, if you have 4, you have S4, which we'll see in the next video. So for 4, how many times 4 can be written? We'll perform it there, so you will understand it. 4 can be written as 1 plus 1 plus 1 plus 1. We leave the first one because we know that's identity. Okay. Then 4 can be written as 1 plus 1 plus 2. Then it can be written as 2 plus 2, right? Then it can be written as 1 plus 3. Okay. And last one is 4 itself. So those are the different ways in which 4 can be written. Then you take LCM of all of those, you get these numbers. And then you find for order 2, then for order 3, and then for order 4. Okay, and that's how you'll find the number of elements of each order inside the group S4. Alright. Then the last topic is alternating group. So this is again very easy topic. Set AN of all even permutations of degree n is a group of order n factorial by 2 for the product of permutation. So for S3 is 3 factorial. For A3 it is 3 factorial over 2 equals to 3. So therefore the number of elements inside A3 is 3. What are those elements? Those elements are all the even permutations. So in S3 you have even permutations and you have odd permutations, right? So only the even permutations will be part of the alternating group A3. Okay, so in S3 we know that we have identity, we have 1 2 1 3 2 3, so we will just write it here. So you have identity, okay, then you have 1 2, don't mind the writing please, 1 comma 3, then you have 2 comma 3, okay, then you have 1 2 3, and then you have 1. Okay, sorry, I'm putting commas in between. These commas do not exist. Okay, let's remove these. because inside the cycle you don't write commas. I just made a mistake. Okay. All right. So 1 2 1 3 2 3 1 2 3 and 1 3 2. These are the 6 elements inside S3. Right. Now A3 will be taking only the even permutations. What are the even permutations? Those permutations that have an odd number of elements. Right. Odd number of elements is this one. 1 2 3. This is odd. This is odd. So these permutations are then even. Right. So this is an even permutation, this is an even permutation, and in the previous video we saw identity is an even permutation because identity is one element which is odd, so this is an even permutation. Therefore alternating group will be what? A3 will be identity comma 1 2 3 comma 1 3 2. That is alternating group A3. Okay, and we can also understand from the formula, and n factorial by 2, which is 3 factorial by 2, which is equal to 3. So 3 number of elements. Okay, again since it's a group, it's following all the 4 properties of group, that is closure, associativity, identity, and inverse. Now note over here is, what if you might ask, what about the odd permutation, that is 1 2 1 3 and 2 3? What about them? These will not form a group. Why won't they form a group? Because it is written here that in the previous video we saw that where two even permutations are, the product of two even permutation is an even permutation, and the product of two odd permutation is also an even permutation. Okay, so when you perform the group operation of closure on any two odd permutations, you will get an even permutation which won't be inside a group of odd permutation, right? That even permutation won't exist in a group of odd permutation, in the set of odd permutation. Therefore it will not be a group. Okay, that set of odd permutations will not be a group, because on finding the product of two permutations that are odd, you will get an even answer, right? And since inside the set of odd permutation there is no even permutation, so it will not be considered a group. That is why alternating group has only even permutations, because only in even permutations this property of closure is true, and the rest of the properties as well, right? So that's how you perform this. Okay, here we see the again, which I just wrote in the previous slide, S3 itself, right? All permutations are 1 2 1 3 and 2 3, and even permutations are identity 1 2 3 and 1 3 2. So A3 is equal to I 1 2 3 and 1 3 2, and order of AN again 3 factorial by 2, which is equal to 3. Now important thing here which you have to remember properly, correctly at all times, because this is what we are going to use in the future videos in theorems as examples, and conversely when we are performing theorems and you do the converse, you will use this example that I'm just going to explain now. So make sure you remember this perfectly. Sn is non-abelian group for n greater than or equal to 3. Product of two permutations may or may not be commutative. This means that in place of n, if you have n greater than or equal to 3, which means that either n could be 1, 2, 3, 4 and so on. If according to this n greater than or equal to 3, if n is equal to 1, right, then Sn is abelian. If n is equal to 2, Sn is abelian. That S2 is abelian. If n is equal to 3 or greater than 3, in that case this group will not be abelian. It will be a non-abelian group. This means that S3, because we are saying greater than or equal, right? So if n is equal to 3, that is S3, S3 which we just talked about is a non-abelian group. That is FG is not equal to GF. Okay, that's basically what it means. It's not commutative. Okay, so S3 is non-abelian. Only S1 and S2 are abelian. S3, S4 and so on are non-abelian groups. Okay, now AN is non-abelian group for n greater than or equal to 4. Now here is the difference. For S3, S3 is non-abelian, but A3 is abelian. Okay, because the condition here is n greater than or equal to 4. So A1, A2 and A3 are abelian. A4 and so on are non-abelian. Okay, this is what will be used. So in future theorems you will be using this statement that the alternating group for the symmetric group S3 is abelian, but symmetric group S3 itself is non-abelian. Okay, this is what you will use. So remember, S1 and S2 are abelian, but S3 and so on are non-abelian. Alternating group A1, A2 and A3 are abelian, but A4 onwards is non-abelian. So in the next video where we will be doing symmetric group S4 and alternating group SA4, both of them are non-abelian. Okay, so remember that. That's all for this video. It was a lengthy video, but I hope the concepts are clear. I tried to make it as easy as possible. So make sure you give it a like, share, and subscribe. And if you have any doubts, type it down in the comment box below. In the next video in this series, we will be tackling S₃ and A₃ along with example. So make sure you check that out in the future. For now, that's all for today. Thank you. Bye bye.